This is the Lab 4 presentation on the Rijke Tube, presented by Benjamin Jensrud for AE 2610. A Rijke Tube is a pulse combustion device, meaning it produces combustion in an oscillatory manner. It consists of a large vertical tube with a propane burner whose height can be adjusted. The air inside resonates within the tube when the flame is properly placed, causing a feedback loop which improves the mixing of the propane and the air compared to open burning. This is one reason why pulse combustion is of interest to engineers, as it allows for more efficient fuel use in engines utilizing pulsating flow. Within the Rijke tube, the pressure will be measured using 3 piezoelectric pressure transducers attached through the walls, and the intensity of the flame will be measured using a photomultiplier aligned with a glass panel in the side of the tube. A control panel on the Rijke tube allows the operator to adjust several parameters. The propellant flow rate can be adjusted with a rotometer providing feedback. The fan at the base of the Rijke tube, whose presence indicates an updraft, induces an updraft within the tube to kickstart the resonance, can be toggled. The burner's height within the tube can be adjusted with a scissor lift, and the current height can be observed by an indicator that moves along a ruler. Finally, a spark plug can be activated to trigger ignition. One control that is not physically on the control panel is a manual pressure relief valve built into the tube itself that allows for pressure to be vented and which prevents the resonance from occurring within the tube. In order to start the experiment, the fan underneath the tube is activated and the propane line is opened to the correct amount. A flame is then ignited using the spark plug. In order to record data at a high enough rate to get frequency data, all of the pressure transducers and photomultipliers are attached to a high-speed data acquisition system from National Instruments that is run at 5 kHz and stores 1 second of data at a time. For our experiment, 4 different configurations were measured, all of which had the fan turned on and the flame ignited as described previously, and all of which were measured over a period of 1 second with the system previously described. The first configuration was at the baseline position with the valve open to prevent resonance. As expected, the flame was steady and did not pulsate. The second configuration was also at the baseline position, but with the pressure relief valve closed. This time, resonance was both visually and audibly present. In the third configuration, the burner was moved 2 inches up and the valve was kept closed. Resonance was still present. In the fourth configuration, the burner was moved slowly upwards until resonance cut out. This occurred at approximately 6 inches above the baseline point. While the valve was still closed in this case, resonance was not present as the flame was no longer close enough to the acoustic note it was previously at to induce resonance. Here, the amplitudes of the photomultiplier and the pressure transducer are shown. The photomultiplier is only significantly useful in configurations 1 and 2, as after this the flame moves out of the line of sight of the sensor and it is no longer able to measure anything useful. The pressure transducers are in units of decibels, and since they are so close to the relatively large they have relatively large values, so it is most significant to analyze the differences between different configurations. One thing that is immediately apparent is the 2 configurations that sustained resonance, 2 and 3, which had approximately 20 decibels higher values in the pressure transducers than the configurations that did not, 1 and 4. This makes sense, as the acoustic pressure fluctuations were possible in these configurations. Similarly, between configurations 1 and 2, the photomultiplier read more than 5 times greater values, indicating the flames burned significantly brighter during pulse combustion than during steady combustion. As expected, the peak frequencies were a measurable value during the 2 configurations in which resonance occurred. The photomultiplier also agrees in configuration 2 when it was accurate with the pressure transducers, enhancing confidence that the measured value is correct. In configurations 1 and 4, the pressure and light were essentially steady state, so the values there are meaningless and come from sensor noise and other sources. As a comparison, the resonant frequency can be empirically calculated using the speed of sound and the length of the tube. Assuming a half-wave fundamental harmonic, the resonant frequency is approximately 94 Hz. This is very close to the value experimentally obtained, and is most likely different due to the higher temperature of the combustion than room temperature, as well as possibly slightly different values of gamma and R for the combusted air. In the zero displacement position, the pressure transducers exhibited measurable phase offsets from each other. This is most likely due to their physical separation. Interestingly, the photomultiplier is offset by 90 degrees, suggesting there is some time delay between pressure and combustion changes. Several important takeaways can be had from this lab. Resonance seems to only occur when the flame is at certain points, meaning resonance is dependent not only on the geometry of the resonant cavity, but also the characteristics of the energy source. Geometry does have an effect though, as opening a hole causes resonance to completely cease. Finally, resonance can significantly impact the intensity of combustion, so it must be taken into account even in designs that do not intend to have any resonance to avoid overstressing the structure.